Hi, hello everyone. Good morning, good afternoon, and good evening to whichever part of the world you are in. A very warm welcome to each one of you. Today's session is on convolutional neural networks, where we will be covering several aspects of building deep learning models using CNNs and its practical use cases in industry. And the most exciting part of the session is it will be delivered by Dipanjan Sarkar. Dipanjan is a lead data scientist at Applied Materials. He's a Google developers machine learning expert. He has mentored several people and delivered numerous expert sessions in the field of machine learning, deep learning, computer vision, and natural language processing. His contribution to the data science community has been nothing but impressive. And also, he was recently featured as one of the top 10 data scientists in India by a popular analytics magazine in India. And I take this moment to congratulate him on this award, and also thank him for joining us on this evening. And with that, I'll hand the session over to Dipanjan. Dipanjan, it's all yours. Thank you.
Hey, Chanukya. Thanks a lot for the wishes. And hey, everyone. Welcome to the session. We'll be covering convolution neural networks today. A lot of nice aspects to cover. We'll be covering some of the fundamental concepts with regard to what is a convolution neural network, what are the key layers involved in a convolution neural network. We'll be also looking at popular convolution neural network operations and also look at some hands-on examples in the form of specific layer operations, as well as how do you use a CNN model for building a image classification system. The slide deck and code, I think the link has already been shared in the chat. So people who are in the chat, feel free to hit this link. You will get all the relevant material in terms of the slide deck as well as the notebooks, which I'll be covering. So would request you to focus on trying to understand the session because everything will be available to you for reference later on.
Dipanjan, before we move on, one quick
Mhm,
thing. I think your voice is a little less audible. That's what people are saying on YouTube.
mhm.
Yeah,
Um, is it better now?
I think so. Yeah, can you come again? Maybe.
Yeah. Can you hear me better now?
Yes, it's slightly better. Yeah, yeah,
Sure, sure.
yeah. Thanks.
Yeah, just let me know in case the audio is less. I'll
Sure.
just try and tune up the volume. Great.
Yeah, sure.
Wonderful. Okay, so the session agenda for today, I'll just give a brief introduction about myself. Since Chanukya has already introduced me, I'll be covering how do you understand what is a convolution neural network, the structure, the different layers in it. We'll also look at the various layer operations in the form of what is a convolution layer, what's a kernel or a filter, what's pooling, what's dropout, and then we'll also briefly touch upon transfer learning in terms of what are pre-trained models and how do you leverage pre-trained models. And obviously, we'll be looking at some hands-on examples in the form of building image classification models, as well as trying out specific convolution and pooling operations from scratch by implementing it using NumPy. And at the end, we'll briefly touch upon the popular applications of convolution neural networks, as in what are the different types of models and how they are being used in the industry. So a bit about myself. As Chanukya mentioned, I'm a data science lead at Applied Materials. I'm also an author. I've published several books in machine learning, deep learning, NLP, transfer learning, and I'm also a Google developer expert in machine learning. Let's dive into the session. So we'll start with understanding what are convolution neural networks. So basically, convolutional neural networks are also known as CNNs. And as you can see, this is a typical structure of a CNN, where you can see it's a hierarchical structure with multiple layers which are interconnected sequentially. And the overall perspective of a CNN is to understand how to learn hierarchical spatial features, considering you're working on image data. And let's say if you're working on video data, there is the aspect of time. So it also tries to learn spatiotemporal features in that perspective. There are two main aspects in a convolution neural network. Typically, it is built of convolution layers followed by pooling layers. And several of these conv pooling blocks are stacked one after the other, after which we have some fully connected dense layers, followed by an output layer based on whether you're building a classification model, a regression model, or an object detection model, and so on. So convolution layers, and we'll be diving deeper into this shortly. This uses what is called as convolution filters or kernels to build feature maps. So the main task of a convolution layer is to perform feature extraction on source images and try to leverage these features to understand various patterns with regard to how is an image structured, what are the key components of an image, texture, edges, corners, and so on. And the pooling layers basically help in reducing the dimensionality after the convolution operation is performed, which means once you apply a convolution filter and extract what are known as feature maps from your source image, the pooling layer helps in downsampling or reducing the dimensionality, which means it helps in compression and also enhancing specific aspects of these feature maps. And one thing to remember is just like any neural network, as you may have had in this bootcamp so far, or learned in this bootcamp so far, or may have read by your own, there are nonlinear activation functions which are typically applied in a neural network because so that it can learn more complex nonlinear patterns. And that is why there will be nonlinear activation functions like rectified linear units, which will be typically applied after every conv layer, pooling layer, and so on. Another interesting aspect is, again, this is optional, is often your model may end up overfitting on your training data. So we have all heard about overfitting where your training performance is really good, but your validation performance is really bad. So the whole perspective here is to prevent overfitting, you can use layers like dropout or batch normalization. And finally, you end up with the fully connected layers or dense layers. And typically you have an output layer, which helps you in making the final prediction. Now let's dive into the main layer components in a CNN. So as you can see, typically CNNs have a stack layered architecture. As you can see, it has multiple convolution blocks, pooling blocks, and so on. And inside each convolution block, it has multiple filters, as you can see here. And these filters are applied on the source image to give you what are known as feature maps. So a convolution layer typically consists of several filters or kernels. And as we'll look into the TensorFlow API shortly, typically you specify the number of filters by a number, like let's say 16 filters, which means it will apply 16 specific kernels or filters on the source image and extract features. So that is where each filter or kernel is passed over the entire image in patches. And the filter is translated across the entire image. And we will see how this translation also occurs shortly. What you need to know right now is this filter is passed through the entire image and translated across the entire image in patches. Let's say 3 cross 3 is an area of the image which we are focusing on, so 9 pixels at a time. And what happens is the filter itself will be a specific dimension, like let's say a 3 cross 3 filter with 9 pixels. So what happens is a dot product is computed and the result is summed up to form one number per operation or per dot product. So in this way, these filters are applied on the source image and we end up with what are known as feature maps. And then what happens is we get a variety of feature maps based on the number of filters which we're applying. So let's say we have one source image and we apply 16 different convolution filters. So we will end up with 16 feature maps. The next step typically is to take in each of these feature maps and downsample them. So that is where we have what is called as the pooling layer, which downsamples the feature maps from the convolution layers. And typically there are various ways of downsampling. You can take the maximum of several pixels and basically output one maximum value pixel. You can take the average, you can take the sum, and so on. But usually max pooling is used, and we'll cover this also shortly as to why do we choose max pooling. And finally, as we discussed, every layer has an activation component to it where feature maps or pooled outputs are sent through nonlinear activations. And these nonlinear activations helps in introducing nonlinearity and train via backpropagation so that it just doesn't end up being a simple linear model. So
Dipanjan,
yeah.
I'm really sorry. So one quick thing, is there a possibility to increase the volume somehow in your machine or something? Maybe a few people are still facing the issue.
Okay, I'm using the same mic, but let me see.
Yeah.
Just give me a second. Yeah, how is the audio now?
Yeah, it's much better. Yeah, yeah.
Sure, sure. Okay,
Great.
so I'll just reshare my screen. Hang on.
Yeah, thanks.
Okay, so sorry about that. So now we'll talk about the convolution pooling operations. So typically a source image can be a grayscale image, which means it will be only a two-dimensional image of a specific height and a width. And basically there will be various pixel values in the image. And the other aspect would be that if you are dealing with a colored image, then there'll typically be three channels, red, green, and blue. And each of them will be a two-dimensional matrix of pixel values. So basically, this becomes like a three-dimensional tensor. And considering a two-dimensional image for simplicity right now, we'll go into how do you work on convolutions on a three-dimensional image shortly. But considering you have a two-dimensional image, as you can see in the screen here, basically it is built of various pixel values at the end of the day. And each pixel has a very specific value depending on the gray level. And what happens is a convolution filter is basically a kernel. As you can see, this is a 3x3 kernel with very specific values. And this is a Sobel kernel, which means it helps in detecting edges. And what happens is this is basically translated across 3x3 image patches, one at a time. And then it computes the dot product, and you end up getting a sum of this, and that becomes your output pixel. So basically, these convolution filters are translated across the image, starting with 301262241. So this ends up giving you one final convolution output. And this is basically a feature map, by the way. So this is your source image, this is your convolution filter, and this is your feature map. So when you apply a 3x3 convolution here, you end up with one output. Similarly, then the filter is translated to this part of the image, which means 015624410. Again, this is convolved with this filter, and you end up with the next pixel value, and so on and so forth. So basically, it translates from left to right, and then it goes down, and again, left to right, so on and so forth, and you end up with one final feature map. And similarly, you apply different convolution filters to get different feature maps based on the number of filters which you specify in your convolution layer. And once you end up with a feature map like this, then you can apply the downsampling or the pooling operation, where let's say you want to apply a 2x2 max pooling operation. What happens is it will take 4 pixels at a time, and it will just output the max value. So in this way, you can see that from this feature map, it has basically downsampled it to this final pooled output feature map. So in that way, you can reduce the dimensionality so that your training doesn't take forever and you don't end up overfitting on your data also. That's the advantage of using the pooling layer. And now the question might arise that why do we need several layers? Why do we need several filters, which I've been talking about so far? So one of the reasons why we need several layers, as you remember, I talked about it in the beginning, is CNN is a hierarchical layered neural network. The reason is so that it can learn a hierarchy of features where each type of feature or each set of features represents very specific aspects about the image. So what that means is, assume you have an input image here. So the convolution layers, which are typically closer to the input image, they will learn very low-level features, which could include things like just some edges or just some very specific textures, as you can see here. Then what happens is, once you take these feature maps and input it to further convolution layers, it tries to combine multiple edges together to form corners, let's say. It tries to combine, let's say, circular objects and tries to identify very specific aspects like, let's say, the eye of the line and so on. And in this way, once you pass these mid-level features into more convolution layers, which are known as the deeper layers, which are closer to the output layer, they will start learning larger structures, as you can see, like a head or a leg, so on and so forth. So basically, in this way, it learns a hierarchy of features, and specific layers learn specific type of features and get activated based on specific types of inputs. And the reason why we need multiple filters is because we just don't want to learn one edge or one corner. We want to learn multiple aspects about the same image. And that is why we use multiple filters to extract different features from the same image at any specific convolution layer. So that's the reason why we need several layers and filters. Now let's talk about the CNN layer operations in some more depth so that people who may have used CNN models in the past but may not have dived too deep into convolution or pooling operations, things should become more clear once we go past this section. So what is a convolution operation? Typically, a convolution operation always starts with what is known as a kernel. And a kernel, as you can see, is basically a matrix of values which can be of specific dimensions like 3 cross 3, 5 cross 5, or even bigger kernels. And the whole perspective or the whole reason for using this kernel is to extract specific features from the image by performing some mathematical operations. And that is where, as you can see here, if this is the source image, let's say we take a 3 cross 3 patch, as you can see here. So basically, this 3 cross 3 patch of the image has various pixel values. As you can see, 29, 20, 25, 24, 24, 46, and so on. And what happens is we do an element-wise multiplication, kind of like a dot product here, with the convolution filter based on the specific positions of this filter or this kernel. And then we end up with a final sum. And this value is basically what represents 1 pixel in the output image. And by the way, this output image is known as what we call a feature map. So the whole perspective here, as you can see, is this specific kernel is known as an embossed kernel, which basically gives what is known as an embossed form of the image. So the whole idea here is to highlight and extract specific features from the image by applying these kernels. And there are various types of kernels which could be used to perform these convolution operations on the source image. And these are some examples which are also available in Wikipedia. Feel free to dive into it in more detail. As to the identity kernel is basically whatever is your input, you will get the same as your output. So let's say this is like your base image. Now, if you want to do edge detection, there are various kernels. Like if you use any of these kernels and you basically convolve it with the source image and you basically compute those sum of the products and you translate it across the whole image, you will end up with these feature maps. And as you can see, the edges are highlighted in these images. Similarly, there are other types of kernels also, like sharpening, blurring, Gaussian blurring, and so on. And the whole idea here is why we use convolution neural networks. So before convolution neural networks became really prominent or became really important, what we used to do was, and people from an image processing background might find this basically in line with what they used to do, is we used to leverage these kernels and manually extract features. And basically, they would be known as feature descriptors. So we would extract edges, we would extract specific transforms. We would then basically build feature descriptors and maybe pass it through a linear model like an SVM model to build a classification model. So the idea here is, instead of you manually sitting and trying to extract specific features and thinking about whether that will work or not, use multiple filters and use a hierarchical layer of multiple convolution layers so that you can extract various types of features from the image and let the model itself learn those patterns instead of you trying to manually extract features using these convolution kernels. So that's the whole perspective of the advantage of using convolution neural networks. So some key perspectives of the convolution layer, as we discussed before, typically we start off with a specific patch of the image, and that patch of the image will be the same size as the kernel. So the kernel is also known as a filter or a feature detector. And as I said, this can be 3 cross 3, 5 cross 5, or more. And this could be filled with either random values, which we usually don't do. We usually fill it with specific values depending on the type of kernel which should be applied. And then what happens is there are a wide variety of filters also which are available, as we saw in the previous slide, where you could detect edges, corners, patterns, you could sharpen it, you could blur it, and so on. And the idea is convolution layers usually have multiple of these filters or these kernels to extract multiple feature maps from the same image. So from the same image, you will get different variants or different features, which basically form the feature maps. And the feature map is basically the output of the convolution operation, just to reiterate again what we just discussed so far. So let's say you have a conv2d function, you pass in an input image and a filter, you should get back the convolved feature map. And this feature map is formed by element-wise multiplication of these two matrices. So every pixel in the output feature map, as we discussed, is formed from this element-wise multiplication of these two matrices, and then basically taking the sum of that, right? And works on the image patch by patch. So as we discussed, it starts with the 3x3 patch, it goes to the next 3x3 patch, so on and so forth. And the kernel size is basically the size of the filter, which is applied on the image patch. And there is also another aspect called stride. So stride is the number of pixels to move horizontally and vertically after you apply a convolution operation. So let's say you start at the source of the image, which is the leftmost pixel, and you apply the convolution operation and you get the final output, 1 pixel in the feature map. To go to the next patch of the image, the default stride is 1, which means it will move 1 pixel to the left, which means it will start with this 0, 0, 0, 1, 1, 1, 1, 2, 2. But if you gave the stride as 2, then it would start from here. So in that way, you could skip certain pixels of the images also as you're going about building these feature maps, and you could reduce the dimensionality of your feature maps without using pooling also by increasing the stride in your convolution layers. So that is where stride is the number of pixels to move horizontally and vertically, and by default it is 1, and we usually use 1 as the stride unless you want to reduce the dimensionality directly in the convolution layer. And as discussed, the activation layer is always there, where once the feature map is constructed, it is passed through, let's say, a ReLU activation function. And typically the positive values are retained and the negative values will be set to 0, because as you remember, ReLU is basically the max of 0 comma x. And if x is negative, basically it outputs a 0. And for those of you who have used TensorFlow, and we will be looking at this code shortly. So this is the TensorFlow API for the conv2D layer. And I just wanted to show this because it is good to check out the documentation also, which you can do later on anyway. But the key components which are very useful for us when we use this conv2D layer is, one is the filters, which basically talks about the number of filters or the number of kernels we want to use to extract features. The kernel size, which basically means what is the size of the filter or the kernel which we want to use. And we just discussed this in the previous sections also, where we looked at a 3x3 kernel. You could use a bigger kernel also if you want. Activation is the type of nonlinear activation to use. Typically, we use a ReLU activation function, the rectified linear unit. And stride by default is it'll move one set of pixels on the right and one set of pixels down as we translate and get those image patches to form the different pixels of the feature map. So by default, stride is always 1, which means the number of pixels to move horizontally and vertically after each convolution operation. But you could increase the stride also, and in that way, you would reduce the dimensionality of the feature map. And padding, there are 2 options for padding. Typically, it is valid or same. So in case of valid, what happens is we don't do any padding around the image. What that means is, let's say I have a 28x28 image. If you apply a 3x3 kernel, the edges of the image, you won't be able to apply a convolution filter. The reason is because the 3x3 kernel, as you can see here, will always start here. So basically, you can see that here we have different values. So assuming, let's say we had padding here, if you apply a 3x3 kernel, it would always start with the leftmost pixel value. And what that means is you wouldn't be able to apply convolution if there was no padding. So here valid means when you're applying the convolution filter, you will always start at 1 row below and 1 column on the right of the image, because that is where your center pixel starts. So basically, you would always start the convolution from here. And that means the outermost row or the outermost boundary or the edge of the image that gets reduced. So basically what that means is 2 pixels would get reduced from your row and the column. That means if you had a 28x28 image and you applied a 3x3 kernel, if you didn't apply any padding, your convolution feature map would be of size 26x26. So that is where if we set the padding to valid, that means it reduces the size of the image after convolving due to the loss of the edges. But you could apply additional padding on your source image and you could retain the size of your image. So that is where if you set the padding as same it would pad extra pixels around the image so that it would retain the original image dimensions after the convolution. So let's say you're the source image of size 28 cross 28. If you apply the 3 cross 3 filter and set the padding as same, it would pad an additional layer of pixels around the image so that you would end up with a 28 cross 28 feature map. In that way, you don't lose the image dimensions from the source image dimensions. So simple convolution is what we have discussed so far, where the operation happens on 1D tensors, where let's say you have a grayscale image of size n cross n. If you want to set a padding, you can put a padding of p around the image if you want to retain the same n cross n size in your final feature map. Typically, you have a filter of size f cross f, let's say, which could be a 3 cross 3. You could set a stride of 1, 2, or more than that, and you would end up with a final feature map. And this is exactly how the convolution operation occurs, where you can see that the filter is basically being transposed from the top, and it starts from the, as you can see in this corner, and it goes one at a time from left to right, and then again 1 pixel down left to right, so on and so forth, and you get the final convolved feature based on the product and the sum which we just discussed. So this is a simple convolution operation which happens on one-dimensional tensors. Now let's talk about color images. So more than often, you will not be dealing with grayscale images, but you will be dealing with color images. So what that means is, instead of a height cross width, you would also have a number of channels, which is basically the volume or the width, let's say. So in that way, we would typically have a 6 cross 6, let's say, is the size of the image. You would have a cross 3, which means 3 stands for one matrix for red, one matrix for blue, and one matrix for green. So basically, those are the 3 channels of the image. So how do you do a volume convolution, as it is known as, where you operate on a 3-dimensional tensor? Because here you don't no longer have just a 2-dimensional matrix. You have a perspective of depth of volume also. So this is where you apply the same filter. Let's say you're applying one filter to get one feature map. So what would happen is you would apply the same filter on each of the channels of the image. As you can see, the weights in all the channels, the kernel weights are the same. So you would basically apply this kernel and you would convolve across the red. You would apply this kernel and convolve across the green and the blue, and you would basically sum it up. And in that way, you would end up with a 4 cross 4 feature map. And again, there is no notion of depth here because we just summed it across all the 3 channels. So that is how you end up with one feature map when you apply one convolution filter across the 3 channels. So just remember, whenever you're operating on a color image, the same convolution filter is applied across all the 3 channels of the image, and it's combined to give you one feature map. And that is another thing to remember, is that what happens next when you want to visualize the full flow of the convolution layer going through the activation and so on. But before we go into that flow, one more thing to remember is what happens if you have multiple filters also. So that is one thing I forgot. So in this case, we just showed that, okay, we have one edge detection filter. We apply that same kernel across red, green, and blue, and we get one feature map. But we just discussed that there could be multiple feature maps because we want to extract different features or different perspectives of the same image. So how does depth volume convolution work then? How do we convolve across all the 3 channels? So basically, it's the same thing. You end up with one set of filters for red, green, and blue. Let's say this is trying to extract the vertical edges of the image. And let's say we also want to extract the horizontal edges of the image. So basically, we'll have another set of filters which does that job, right? And what we'll do then is we will apply the same convolution operation for this set of filters on these 3 channels of the same image. We will end up with one 4 cross 4 feature map. Similarly, we will end up with another 4 cross 4 feature map because of this convolution operation. And remember, here we haven't done any padding, so we are losing the edges of the source image, and we end up with 4 cross 4. If we had set a padding equals same, then we would end up with a 6 cross 6 feature map. So the whole idea here is, if your source image is 6 cross 6 cross 3 and you apply, let's say, 10 filters, you would, of 3 cross 3, you would end up with 4 cross 4 cross 10, basically 10 feature maps. So that is how volume convolution happens, where you apply multiple features. And this is the high-level operation flow of how things work across a full convolution layer, where you start off with a source image, You have multiple filters here where each of these filters are applied across all the channels of the source image. You then sum it across and end up with a feature map for each filter. You pass each of these feature maps through the nonlinear activation, and you then end up with basically getting the final output of the feature map. And then, as you can see here, we have 4 cross 4 cross 2 because we applied 2 filters. And basically, then these feature maps would go into the next pooling layer, into the next convolution layer, and so on. And what is pooling? So we discussed about pooling. As you can see here, pooling helps in reducing the number of parameters by downsampling. What that means is we would take specific patches of the image again, depending on the size of our pooling layer, where if we, let's say, set the pooling layer to be 2 cross 2, we would look at 4 pixels at a time, and we would take the maximum value from it. And that basically becomes the output of the downsampled feature map. So typically this would be a feature map coming from a conv layer. This would go into the 2 cross 2 pooling layer, and we would end up with a smaller sized feature map. And the reason for applying pooling is reduction in parameters, which help in faster training and helping in preventing overfitting. And like I said before, there are various types of pooling available. It is not like there is only max pooling in general. There are various types of pooling operations like sum, mean, max, and so on. But typically, max pooling is the one which is preferred. One of the reasons is taking a max of pixels is much faster than doing a mean or a sum if you think from a computation perspective. And also, it has proven to give a much better performance than mean or sum. That is what even I've seen based on some of my projects, which I've done kind of a while back. And the other aspect is it helps in enhancing the key aspects of feature maps in terms of highlighting the specific activations which are, or the pixels which are being activated. So that is another reason for applying this max pooling. And pooling size, as I discussed, is the number of image pixels you consider or set of these pixels to do the downsampling. Dropout, I will touch upon this briefly. I'm hoping that you all may have heard about this before. So dropout is a technique where randomly selected neurons are completely ignored during training. So randomly X%, like let's say if dropout is 0.3, X% of these neurons or units will be completely ignored during training. And this helps in preventing overfitting because this is randomly done. And basically, this is a regularization mechanism. So let's now look at some of these CNN layer operations with some hands-on before we dive into the modeling phase of things. So the repository is there and the notebooks will be there in the tutorials folder. So feel free to access it. I will be opening it up in Colab and kind of going through the notebook now. So the whole idea of this is to understand the two main layer operations in a CNN. How do you actually code it out? The convolution layer and the pooling layer. So let's say we start with loading up a sample image, which I have, and I've shown this in the slide also. So as you can see, an image at the end of the day is just a bunch of pixels. And this is a grayscale image. Basically, I've converted the image to grayscale to keep things simple. So there are no channels here. It is just a matrix of pixel values of size 225 cross 225. And basically, this is an image of a line, as you can see here, a painting. Now what we'll do is we'll implement our own convolution layer. So what we'll do here is we copy the source image because we want to generate a feature map. We don't want to modify the original image, obviously, that is our source image. So we create a copy of the image. We get the dimensions here. Now what we do is basically that patch generation and then that computation, if you remember. So for every pixel in our image, right, for every pixel, basically x comma y, if you think about it, because x and y is basically, if you remember, your width is x and your y is your height, if you think about it. So for each x, y value, what we want to do is we want to apply a 3 cross 3 convolution. So initially our convolution operation value is 0 because we want to apply the convolution and then get that feature map pixel value, which goes into 1 pixel in that final feature map. So as you can see here, the source image patch is basically this. So if you want to apply a convolution on a specific patch of the image, obviously the center pixel of that image will be x comma y. And if you think about it, the surrounding pixels will be x minus 1 comma y, x minus 1 comma y minus 1, x comma y minus 1. So you get the point. Assuming your y is basically your height and your x is your width. So if you go 1 pixel to the right of x comma y, it will obviously be x comma 1 comma y. And if you go 1 pixel to the left, it will be x minus 1 comma y. If you go 1 pixel up, y gets reduced by minus 1. And if you go 1 pixel down, it gets increased by plus 1. Because if you remember, the corner of an image always starts at 0 comma 0. So this is, if you look at these three values, then these three values and these three values, this is one patch of the source image. And on that, I will be applying the convolution filter, if you remember. So the convolution filter is a 3x3 matrix of values. So this is how it is represented. And this basically we do the multiplication and compute the sum, and we get the new image xy pixel value. And this new image is nothing but our feature map. And that is exactly what I'm doing here, if you see, in terms of the mathematical operations, where I am taking the initial convolution value, the feature map pixel value, which is set to 0. And then I'm going on adding each of these multiplication operations, right? The operation from it. So x minus 1 comma y minus 1. Basically, I will multiply this by the pixel value or the value of the filter at 0 comma 0. Similarly, 0 comma 1 we multiply by x comma y minus 1, so on and so forth. And once all of this is done, we compute the sum. And then what we do is we normalize the filter weights so that they add up to 1. This is just a basic normalization strategy. And after that, we do one more thing, which is known as the pixel clipping. So in case for some reason our pixel value of the convolution operation has led to it going beyond 0 or above 255, we clip it to 0, between 0 to 255. And then what we do is, for the new image is a feature map. At the x comma y position, we apply the convolution value, the pixel value basically. So you can imagine that every 3x3 patch of the image ends up being just one convolution pixel value in the new image. And this happens across the full image, as you can see, starting from the leftmost pixel of the image right till the bottom rightmost pixel of the source image. And once this function is defined, we can then try and apply different kernels. So now we call our convolution 2D function, apply it on a source image, and we pass in an edge detection kernel, a Sobel Y kernel, and this helps in detecting the vertical edges. As you can see here, the vertical edges gets enhanced. Now, if you change this to the Sobel GX kernel, which is basically this, then what happens is the horizontal edges will get enhanced, as you can see here. So you can see the difference. Here, the vertical edges are very enhanced, but here, the horizontal edges get more enhanced. And then there are other edge detection kernels, also like the outline kernel, which kind of tries to enhance every edge present in the image. We discussed the emboss kernel briefly, if you remember, on that slide deck, that specific slide. So that will emboss or build an embossed version of the image. And similarly, you have other filters like Gaussian blur, where you can see this is basically a blurred, slightly blurred version of the original image. You can even sharpen this image by applying the same conv2d function and applying a sharpening kernel. And you can see that this is much more sharpened now. So you can see that just by some simple operations here, some simple mathematical operations here, we are able to build our own convolution layer where you can apply and try out different types of filters, play around with it, and see what is the output. Similarly, we can apply a max pooling layer also. So the basic aspect of max pooling is that the downsampled feature map will be halved in size, considering we are doing a 2x2 max pooling to keep things simple here. So that is where we initialize a new image with the dimensions of the x by 2 and the y by 2, so that it's half the size of the original image dimensions. And then what we do is we go through the full image, go through the full source image. In this case, the source image will be the output of a convolution filter operation, which means it will be a feature map. And as you can see, we take 4 pixels at a time. So we take an image patch of 2x2, which means x comma y x plus 1 comma y, x comma y plus 1, the bottom pixel, and x plus 1, y plus 1. So we take 4 pixels at a time. We append this to our list of pixels, and then what we do is, at the specific position in the downsampled feature map, the new image, just take the max value. So 4 pixels at a time get compressed into the maximum pixel, or 1 pixel. And that is our pooling operation. And then you can see, once we apply the max pooling operation on the output of the feature map, you can see that the specific places or the specific edges get more enhanced. And you can compare the size of the image also. The original image size was around 225 or something, and now it's almost halved. So that is the aspect of pooling. It downsamples the image. And you can see that the blurring becomes more enhanced when you apply the pooling. Similarly, the sharpening also gets more enhanced because it's obviously taking the max pixel values around these regions. So that concludes the aspect of the layer operations in terms of the core layers of the CNN, the convolution layer and the pooling layer. So hopefully this was useful. Now we'll go into the modeling perspectives. But before we build a convolution model from scratch using the same conv pool layers, we also want to touch upon briefly about transfer learning. Some of you may already know this, some of you may have heard about this. So today we will be building a convolution or a CNN model from scratch to build an image classifier, and we will also leverage a pre-trained model and see how that performs. So what is transfer learning? Transfer learning is where, instead of always building a model from scratch on your data set based on the problem you're solving, instead of doing that in isolation, why not leverage a pre-trained model, which, let's say, was already built and already trained on a huge amount of data, so that the layers of that model are already tuned to extract the right kind of features. So you take in that pre-trained model, and then you leverage it to solve your own problem and apply it on your own data set. So this knowledge is basically the pre-trained layer weights of your deep learning model, which you will be leveraging. And the whole idea about transfer learning is, take a network trained on a different domain for a different source task and apply it for your domain and your target task. So what that means is, you have source labels, you have a source model, let's say, which was trained on ImageNet. So what is ImageNet? ImageNet is basically, you can Google this later also, ImageNet is a competition where there are, let's say, millions of images and around 1,000 classes. And the whole idea here, it's known as ImageNet 1000 or ImageNet 1K. So a lot of companies and a lot of universities across the world try to build the latest state-of-the-art convolution neural network to reach the highest accuracy. And the model we will use today is the VGG19 model. VGG stands for Visual Geometry Group, which is a group at Oxford University, which has built this model. And this had broken the benchmark score a couple of years back. There are more complex models also, like ResNet, Big Transfer from Google recently, and so on, but we won't cover that, considering this is a beginner-friendly session. But coming back to the point, why not take a pre-trained deep learning model, which was trained on, let's say, millions of images of thousands of classes, like the ImageNet data, and then solve the problem of apparel classification, which is the problem we'll be solving, where we'll be taking the fashion MNIST data set, which is a very simple data set considering 10 different types of clothing. And the whole objective here is to predict what is the type of clothing, whether it's a shoe, whether it's a shirt, and so on. And the idea is, you are already having a model which was trained very well to recognize different types of classes, thousands of classes. Now take in that model and fine-tune that model and leverage it for your own problem, and try to transfer that knowledge and adapt it for your own problem. And that is exactly what we will also do as the second part of our modeling notebook. And there are two approaches to transfer learning here. One is, you take the source model, the source pre-trained model as it is. You don't tune any of the layers to adapt it to your data set. What you do is, you just pass in your new images and you extract the final features, and then you build a downstream model. That could be a dense neural network model, that could be a SVM model, that could be anything. So basically that means you just freeze that pre-trained model and only use it to predict on the new images. And by predict, I mean just extract features and use those features for your own task. The other thing is, you try to adapt that model's knowledge and tune it to your own data, which means you open up the layers of that pre-trained model for fine tuning, and you change the weights of those pre-trained layers and try to adapt it to your own data as you start training. So that is what we will be doing, where we will be fine tuning that model on our data. And why are we talking about pre-trained models suddenly? So the reason for the pre-trained model discussion is because often training deep learning models from scratch can take a lot of time. And the other reason is also pre-trained models have been trained on a lot of data and specialized for performing specific tasks, like let's say classification, object detection, and so on. And so if you have less amount of data, often leveraging a pre-trained model can give you a better performance than building a model from scratch. So that's the whole reason for bringing in this perspective about pre-trained models. But again, something to remember here is that that is not always the case. You need to be very careful that transfer learning is not a silver bullet that you think that, okay, I'll just take a pre-trained model and throw some data at it. Often you may need to pre-process your data. Often you may need to analyze your data to really understand whether this will really work directly, or you may need a more custom model. And as discussed, you can use a pre-trained model to just extract features or plug in more layers and fine-tune that full network and do specific downstream inference in the form of classification, segmentation, or object detection, and so on. And transfer learning, again, as you can see here, these are various types of models which have been released over the years. And these are all state-of-the-art models for computer vision. Nowadays, you also have pre-trained models, pre-trained language models available for natural language processing. More specifically, the transformer models. I think some of you may have heard about it, like BERT and so on. And you can leverage those models, which have been pre-trained on a lot of data, and adapt it to your own tasks, like named entity recognition and so on. But again, I digress from the true nature of the talk. Since we are talking about CNNs, that will be for another day. The model we will be using in the pre-trained phase of our training will be the VGG19 model. As I said, it's from the visual geometry group. So we discussed about a convolution neural network. It's basically a bunch of stacked convolution and pooling layers followed by some dense layers and the output layer. So similarly, the VGG19 model is a 19-layer deep learning network which has been trained on the ImageNet data set. And you can see that there are various convolution layers followed by max pooling layers. And these layers have specific names also, which you can refer to in the model and extract specific feature maps if you need to. And there are basically 16 convolution layers, which use 3x3 convolution filters along with some max pooling layers. So after the conv pool blocks, you end up having two dense layers or two fully connected dense layers, which have 4096 neurons or 4096 units in each layer, followed by an output layer which has 1000 units. And why does it have 1000 units? Because like I said, the ImageNet dataset had 1000 different classes, and that is what this model was trained on. But for us, we won't care about this part of the model. We will care about this part of the model because we care about extracting the right features, and then we will plug in our own dense and output layers so that we could make the prediction based on our classes. So our output layer would be of 10 units instead of 1000 units because we will be predicting 10 different types of apparel. So now let's dive into the last part of this session where we will go through the journey of building two CNN classification models to classify 10 different types of apparel, basically on the fashion MNIST data set. We will start with building a CNN model from scratch, a simple two-layer CNN model, and then we will go into using this 16 to 19 layer more complex pre-trained model, and we will compare the performance. So this is basically the second notebook here. In case you are interested, you can refer to it later. So the whole perspective about the CNN model is to take in those images, pass it through all these conv pool layers, and then make the final prediction as to what is the class of that image. So we will be leveraging the tf.keras API style, and it is recommended that you try this out on TensorFlow 2. I'm using Google Colab, so by default it has, I think, TensorFlow 2.3, which I presume is the latest version. So it is recommended you try this out on TensorFlow 2 because now you don't need to import Keras specifically or install Keras specifically. You already have it available as a part of TensorFlow itself. And future updates to the Keras API will be made in the TensorFlow 2 package. So it's recommended you use that. So some basic dependency inputs I'm doing here. And as you can see, the TensorFlow library I'm using, its version is 2.3.0, just for reference. The main objective, as I said briefly before, is to build an apparel classifier. We won't be deploying it today, obviously, due to the lack of time. But for folks who are interested, I do have an article on this. So I will link that to you later, or you can find that on my Medium in case you want to see how you can deploy this model at scale. But today's perspective is to understand how to build a CNN model from scratch. So we will be building a simple apparel classifier by training models on this very famous fashion MNIST data set. And this is an open data set out there. And the whole premise of this problem is it's a classification problem. You have 60,000 images of different apparel, which is your training data set, and you have 10,000 images as your test data set. Every image or every apparel image is a 28 cross 28 grayscale image. And the total number of distinct types of apparel is 10, which means you have 10 classes. And basically, it is a multi-class classification problem where you have to predict one out of the 10 classes for each and every image. And we will be building two models again here from scratch. One is a simple CNN, which we will train from scratch. And the other one is we will take in a pre-trained VGG19 CNN model. We will add in our own layers and we will fine tune that model. So the data set is already available in TensorFlow. You can just refer to it as tf.keras.datasets.fashionMNIST. And then if you call the load data function, you will end up with tuples where each set of tuples is basically your train images and the train labels, and correspondingly the test images and the test labels. For ease of understanding, I have kind of named these classes here so that we can refer to it in a more easy to understand and a more interpretable format when we evaluate the model performance, as well as maybe visualize some of those images. This is in order, which means images with a label 0 is basically a t-shirt or a top, label 1 is trouser, label 9 is ankle boot, and so on. And as discussed, 60,000 training images, grayscale images of size 28 cross 28, 10,000 test images of size 28 cross 28. We already covered about the CNN model and the hierarchical layered structure. So in this section, we will be training a simple CNN model from scratch. Now, one thing to remember here is that CNN models or the conv layers will work on channel data or tensors, which means you need to specifically mention whether it's a one channel image or whether it's a 3-channel image and so on. So that is where we will reshape our data before we train our model. Here, since we are working on grayscale 1-channel images, what we are doing is we are just reshaping it to mention the channel number of the channel size explicitly. So instead of 28 cross 28, it becomes 28, 28, 1. So what that means is basically if you consider a NumPy list of lists, it's like wrapping another list inside your list of 28 cross 28 matrix pixel values. That's all. So that's what we do. And we end up with a train and test shape like this. This is some basic visualization code, as you can see. So this is how our sample training data looks like. Like this is an ankle boot, this is a t-shirt, and so on. And as discussed, every image is of size 28 cross 28 pixels. Now we will build a CNN model architecture. So our input data shape is 28 cross 28 cross 1. 1 is because we have only one channel, and 28 is our height, and 28 is our width. We use the sequential TensorFlow model API. There is also the functional API. Sequential is easy to use, easy to understand. Functional is slightly more complex to understand, but it's very customizable. The perspective here is to build a CNN model and demonstrate how it works. So let's keep things simple. We define a sequential model. Now what happens is you can build a layered architecture here where you can keep appending layers to the sequential model, which is like a empty blueprint. You can think of it like that. So what we do is we define the conv pool layer, the first set of conv pool layers. So this is, if you remember from the slide, we are using that same exact API here. TensorFlow keras layers conv2d, we are saying that there are 16 filters, which means 16 feature maps will be extracted from the source images. The filter or the kernel size will be a 3x3 kernel, and use a normal stride of 1 on the right and 1 on the bottom as you translate through the image. Use a nonlinear ReLU activation. Padding is valid, which means don't pad the image and don't retain the same dimension of the image. It is okay to basically lose the edges and reduce it. And max pooling after the conv layer means after we get the 16 feature maps from this, pass it through the max pooling layer, and you end up getting a downsampled version of your convolution layer. So that is basically your 2x2 pooling, which is being applied. So once the output comes from this set of the conv pool layers, what we do is we apply a second block, because as we discussed, it's like a stacked conv pool hierarchy. So then we again apply a conv2d layer, and we say this time apply 32 filters. And then same 3x3 kernel, ReLU activation, one stride, and valid padding. And after that, again, apply a 2x2 max pooling. So in short, we apply two sets of conv pool blocks. And after that, we flatten it, which means we get a final flattened feature vector from the two-dimensional feature maps across the image. And once we flatten it, then we apply two dense layers, just like you remember it was there in the VGG model. But there they had 4096 hidden units or neurons, but we are keeping only 256 neurons because we are keeping things simple. And between each dense layer, we keep a dropout layer of 0.3, which means lose 30% of the neurons randomly whenever you're training across the epochs. And ReLU activation is being used in every layer because there's a nonlinearity. The output layer will have 10 units because we want to predict 1 out of the 10 classes. And it is a softmax activation because we will be predicting 1 of them. And we'll be getting the class probabilities, which will be normalized from the logits. So based on your deep learning bootcamp, I think by now you should be aware about this. And for people who know the basics of neural networks, I think you know that once you get the logits, you can get the probabilities, the normalized values from 0 to 1, which the softmax function helps in squashing and giving you. And the other things are regular sparse categorical cross entropy, because we'll be predicting the specific label. We'll use the Adam optimizer and just an accuracy metric. And this is where things become easy for you to understand. So our source image was 28 cross 28 cross 1. We applied 16 filters. So you can see we end up with 26 cross 26 cross 16 because there are 16 feature maps. Then they get halved because we're applying a 2D max pooling. Then we lose 1 pixel again and end up with 32 feature maps because we applied a second conv layer. So I hope things are becoming more clear now. And then again, this gets halved because we're applying another max pooling of 2 cross 2. And then what happens is these 32 cross 5 cross 5 feature maps, basically you just flatten it and you end up with a big feature descriptor or a one-dimensional feature vector of size 800. And then you pass it through to dense layers of size 256. So this model.summary is a nice way for you to understand how are your parameters changing over time, how is your layer structure and dimensions of the tensors changing layer by layer. And then we basically do a model training. So what I'm doing is I'm saying, let's train a model for 100 epochs, but obviously 100 epochs would be overkill here because the model may start overfitting soon. So what I do is I put an early stopping callback, which means that I want to monitor the validation loss. So I will use 10% of the training data as a validation set. And what that means is out of 60,000 images, I will be training on, let's say, 90% of 60,000, which means around 54,000 images. And I will be validating the performance in every epoch on 6,000 images. And I will be computing the loss and the validation accuracy. So what I'm saying is across 2 epochs, if the validation loss doesn't improve, that means maybe our model is slowly starting to overfit. So just stop the training then and there. That's early stopping. And restore it to the last best model with the best validation loss. Again, multiple ways of using early stopping. This is not the only way, but this is a pretty decent way, which works well. And one thing I forgot to mention is you have to scale your images. So our pixel values range from 0 to 255. So we normalize it to make it between 0 to 1, because as you know, neural networks like to work with small values or small numbers. and normalized inputs help the neural network converge better and doesn't take as long to train. And then we fit the model with a batch size of 32, our scaled input training data and the training labels. We say that use 10% of the data for validation, and we pass in a callback because while we are training for 100 epochs, we want to stop the model training as soon as we don't see an improvement in validation loss over 2 consecutive epochs. And as you can see here that the model is training across all these epochs, and after 0.2477, the validation loss starts increasing. And then basically we figure out that it's time to stop the training. And after around 8 epochs, the model stops training. And we reach a pretty decent accuracy around, we are reaching close to 90% accuracy, 90.5 or 91% validation accuracy. And training accuracy is also around 91.5 to 92%. So they are kind of close to each other. So definitely not overfitting too much. And these are our learning curves, by the way. So if you do history equals model.fit, basically you end up with a nice dictionary of values, and you can just call a data frame on history.history. That's like a neat trick you can do. And then you can just subset out specific columns of the data frame and visualize these learning curves that, okay, across the epochs, how is the training loss looking? How is the validation loss looking? And how is the accuracy and the validation accuracy looking? And in that way, you can see whether you're overfitting too much. How is the training happening? Is your learning rate too high that your learning curve is fluctuating too much? So in these ways, you can debug your CNN model. And then obviously now we have built and trained our CNN model from scratch. It's time to put it to the test literally. So we scale our test images, the 10,000 images, we scale and normalize it, and then we predict on this. And as discussed, that the softmax basically returns you the class probability. So every image will end up having a prediction vector of size 10. And these 10 are basically the class probabilities of the model predicting that what is the probability of this image being class 0, class 1, class 2, and so on. And the idea is to take the maximum probability from this, but not just take the maximum probability, but find the index or the position by doing an argmax so that we could figure out that what is the class label for that. And that is exactly what we do here. We apply an argmax on the predictions across axis equals 1, which means applied for each and every prediction. And then we end up with the class labels, where if you remember, class 9 is like the ankle boot and so on. And then we basically leverage those class names I had built before in that class names list. And I call the classification report and the confusion matrix. And in this way, you can visualize a nice precision recall F1 score accuracy across all the classes, as well as look at the average score. And you can see here that we get a decent score of close to 90 to 91%. And that's pretty decent that using a simple 2-layer CNN model, you could get this kind of an accuracy. And you can even view the confusion matrix in a nice interpretable way. And you can see that shirt is obviously getting confused with t-shirt, it's getting confused with pullover, getting confused with coat, which makes sense. That's the reason for these misclassifications. So in this way, you could debug and see that which are your classes most prone to misclassifications and what could be the reason behind that. Another interesting thing we could do is figure out that how is the CNN model actually learning? So what is it actually seeing? I mean, once we see a trouser, we can say that, okay, because the trouser has a crease, the trouser has 2 specific structures and so on, we can say that that is why it's a trouser. So intuitively, we can think about it because we have seen so many trousers before. But what is the CNN model actually learning so that it's basically getting activated? That activation map, feature map gets activated, and then it basically says that it's a trouser. So that is where we can extract out the feature maps, or rather I would use the word activation maps. After the feature map goes through the activation function, we could extract out those activation maps from the specific layers in a CNN model, and we could try to see that which pixels are being highlighted. That is a simple way to see that if we pass an input shoe image or if we pass an input trouser image, which parts are getting highlighted. So that is exactly what we will try to do. Again, this is an area which is also called as interpretable machine learning or explainable AI, there are a lot of packages out there like Shapley values, GradCam, and so on. But we won't be going into too much detail about that in the interest of time, as well as the nature of the session. But we will be looking here at how you can use simple ways to extract activation maps and visualize that. So here, as you can see, this is the class labels of my first 100 rows in my test data, or first 100 images in the test data. And as you remember, class 9 was basically ankle boot. So we pick specific instances from our test data that, okay, pick up image 0, pick up image 23, pick up image number 28. And then what we do is we build this specific functional model, which is basically what it's trying to do is it is taking the input from our source sequential model. And what it's trying to do is it's trying to basically extract out the activation maps of each and every layer. So that is exactly what we'll try to do. And we take in these three same images of ankle boot, and we say that we want to visualize filter number 13, and we want to see how it's looking like across these three images. And what we do is we want to visualize that the journey of filter number 13 from conv layer 1, pool layer 1, conv layer 2, pool layer 2. If you remember, we had two sets of conv pool layers. So we want to visualize 4 feature maps or 4 activation maps of filter number 13. If you remember, initially we applied 16 filters and then 32 filters. So filter number 13 is what we are choosing. And once we use this code, we are basically predicting using this activation model, which we defined here. And then we are trying to pass in the specific image, in this case, image 0, then image 1, which is image 23, and then the next image is image 28. And we are visualizing the filter number 13, and we are trying to visualize the journey of that across those sets of conv pool layers. And you can see here that the ankle boot, this is the output of the first convolution layer. If you remember, the size was 26 cross 26. Then it was 11 cross, then it was, I think, 13 cross 13, if you remember. And then it became 11 cross 11, and then 5 cross 5. If you remember the model summary, I'll just scroll above just to recap. Sorry about that. But if you remember, initial conv feature map was size this, pool size was this, then the next conv size was this, and pool size was this. And this is where we are visualizing these feature maps. And you can see that filter number 13 really gets activated, and it can kind of visualize the outline of the shoe. And that basically gives you the perspective that this filter will get really activated whenever it sees a shoe. And that helps it basically predict ankle boot correctly. Similarly, let's say we apply the same convolution filter. We apply the same filter number 13 on another set of images, which are basically trousers. So now you can see that we are seeing some activations here and there, but there is nothing which is really prominent here across all these conv and pool feature maps. So what we do is we change the filter number to 3 now, let's say, instead of filter number 13, because 13 was activating the shoes. And now you can see the outline of the trousers coming up. So what that means is convolution filter number 3 is very influential for the model to predict trousers accurately. So in this way, you can play around with different filters in this code, play around with different images, and really try to understand your model as to how is it really predicting a trouser, or how is it really predicting an ankle boot or a shirt, and so on. So this is a nice way where you can just use a simple functional Keras model, output out the feature map of each conv and pool layer, and just visualize it. And again, here we had to write a lot of additional code, but there are libraries out there which you can use directly and pass in your images and get these things without manually coding it. But the reason for showing this is, as you can see, it is not that difficult. The whole idea is to just visualize every feature map separately. Now, the last part of a session is we built a CNN model from scratch, and we trained a CNN model from scratch, basically a 2-layer CNN model. So now, what if you wanted to use a pre-trained model? What if you wanted to explore the power of transfer learning? So this is where we leverage this VGG19 model, as we discussed before, where instead of now having just 2 sets of conv pool layers, we will have these 16 conv pool layers interspersed with these max pooling. So 16 conv layers, as you can see, each of these interspersed with the max pooling layers. And then we will put in our own fully connected layers and the final output layer having 10 units. So something to remember is the ImageNet challenge was done on color images, which means RGB images of 3 channels. So the default fashion MNIST data will not work on it because it's a grayscale image of only 1 channel. So you need to reshape your data and make it in the right format so that you could pass it to the VGG19 model. By default, the VGG19 model, I think, accepts images of size 225 cross 225 cross 3, which means color images of size 225 cross 225. But the lowest dimensions of image it accepts is 32 cross 32. So we need to do 2 things. One is reshape the data to make it a 3-dimensional tensor and RGB tensor. And the next thing is resize the image to upsample it or increase it from 28 cross 28 to 32 cross 32. So those are the 2 operations we first need to do before we dive into the modeling. Else, your model will get an error. It's not like you just dump the data blindly into the model and it will work. So those are the things you need to keep in mind. So we use a simple NumPy stack operation, which means take that same 28 cross 28 pixel values and just replicate it 3 times. And you end up with a 28 cross 28 cross 3 channeled tensors for each and every image. So now instead of 28 cross 28 cross 1, you have 60,000 training images of 3 channeled images, same for the test data. Then we need to do a resize. So here we are doing a cubic interpolation. There are various types of interpolation to upsample an image, where you can use linear interpolation, bicubic, and so on. And we are using intercubic here, cubic interpolation from OpenCV. And what we are doing is we are basically resizing it to 32 cross 32. And that is where we set the image dimension to 32 cross 32. And then we pass in our resize image array function. And we resize every image. And now we end up having 60,000 training images of size 32 cross 32 cross 3. And similarly, 10,000 images for the test data. Now our data is ready to be fed into the pre-trained model. So to build to leverage transfer learning, first we need to build the cut VGG19 model. I call it the cut VGG19 model because we are cutting off the last few layers. So we set the input shape of our data to 32 cross 32 cross 3. We download the VGG19 model. You don't need to download the weights manually. You can just call TF-Keras applications VGG19, that is the module, and then call the VGG19 class. Mention the weights as ImageNet, which means each of the layers of that model will get preloaded with the ImageNet weights. And you set the include top equals false, which means that the topmost layers closest to the output, which includes those 2 dense layers of size 4096 and that 1 output layer of size 1000, they will not be included. So only the conv and pool layers will be included. And you set the input size also so that it gets ready to accept input images of your own dimensions. And as you can see now, we have all those conv and pool layers across the VGG19 model. And the image is basically journeying from size 32 cross 32, then 64 filters are being applied, 128, 256. Some downsampling is also happening with max pooling every now and then. And we end up with this. So what that means is we have removed the dense layers. And then what we want to do is we want to do fine tuning, like I said. There are various ways to do fine tuning. Like some people will say you shouldn't fine tune the initial layers closer to the inputs because they learn more generic features, and you should fine tune layers closer to the output because they learn very specific features with regard to your data. But you could even fine tune the full network with a lower learning rate. And that is exactly what I've done here. So what I'm saying is that make each and every layer in the VGG model as trainable. Don't freeze the weights so that when you pass in your own data, backpropagation will happen and the weights of all these layers will also get updated in every epoch. And that is exactly what I validate here, that, okay, every layer should be true in our VGG model. And then we build a high-level sequential model where the first component of the sequential model is our VGG layers, those conv pool layers. Then we add in the flattened layer, and then we add in the same dense layers with the dropouts and the final dense layer with the 10 units for the final output layer, basically. And as you can see, the only difference here is by default, the learning rate is 1e minus 3 for Adam, but we have explicitly set the learning rate here to 2e minus 5, which means 2 into 10 to the power minus 5, which means we have set a far lower learning rate so that we don't suddenly change the weights of those pre-trained layers and basically destroy the pre-trained knowledge which was there. We slowly update it and get it tuned to our data. And other things remain the same, by the way, with the loss function and the metrics. And this is our final model. And then we keep the training exactly same as before, where we scale our data, we keep the early stopping callback, and then we fit our model. And once we do it again for 100 epochs, we have put the callback. So as you can see, after typically after 7 epochs, it stops because the validation loss basically started increasing. And then we restore the model weights from the end of the epoch. And what happens after that is we plot these curves, as you can see here. And as you can see, in this case, we have reached close to 94% training accuracy and around 92% validation accuracy, which is almost like a 2% bump from before. So that is where on benchmark data sets, it's really easy sometimes to reach 85 to 90% accuracy, but getting that next 1 to 5% accuracy improvement can be really time consuming. And that is where researchers spend months to come up with new architectures, which basically beat the previous benchmark and become the next state of the art model. And then we evaluate the model performance on the test data in the same way, scale the test data, predict it, get those softmax probabilities, take the argmax to get the specific indices, which give you the class label, and then pass it through our classification report and the confusion matrix functions. And you end up with the performance where you can see accuracy earlier was around 90%, and F1 score was ranging from between 90 to 91. Now you have around 92%. So it's basically roughly a 1.5 to 2% improvement in the performance. So that basically brings us an end to this notebook. Hopefully this gave you an idea about how do you build a CNN model from scratch by stacking those layers. What are each of those parameters in the layers? Do refer to the TensorFlow documentation whenever needed. It's not like you have to remember everything. And you also saw how we loaded a pre-trained model using TensorFlow Keras applications, then the specific module for the pre-trained model, and then set the trainable to true for the layers. You could keep it as false also if you want to freeze the weights. And then we plugged in our own layers using the same sequential model API, and we checked the performance. So that brings us an end to the hands-on examples. Now, coming to the last part of this session, there's just a one slider on different applications of convolutional neural networks. I won't be talking particularly on ways in which it's being used. You probably have read a lot of blogs or you have seen a lot of things online in terms of facial recognition, disease prediction, and so on. But I'll briefly talk about things which will be useful for you as to what are the downstream machine learning or deep learning applications where CNNs are being used. So CNNs are being extensively used for classification and regression problems, where you can use them in vision problems with image and video. You can even use CNNs for text classification, by the way. It's not just restricted to images, because at the end of the day, it's just a convolution operation which is being followed. So you could even apply it on text data. You could even apply it on audio data by translating audio signal data into MEL spectrograms, which are basically visual representation of the signal data, and then apply CNNs on that. There are a lot of data sets online like Google's audio set, and there are many data sets on Kaggle also, where you can see a lot of people competing and applying CNNs to do audio classification. Object detection is another interesting use case where you can detect objects in images and videos by doing bounding boxes. Most of you may have heard of the YOLO model. So there is again a whole journey for object detection where you have single shot detectors, fast RCNN, faster RCNN, YOLO's different versions, Detectron, I think from Facebook, most probably, if I'm not mistaken. So every time someone or an organization comes up with a more slightly more complex, but a better model. And you can definitely see that convolutional neural networks will be something which is used extensively there. You can use them for image segmentation. There are models like fully connected convolution networks, and you also have I forget. There's another model. Yeah, unit. So there are unit models also which are extensively used for segmentation. Again, conv pool blocks used a lot there, where you can segment key entities in an image. Speech processing and modeling. So again, conv models along with recurrent neural networks used extensively for processing and modeling on speech, like automatic speech recognition. So most of those speech recognition models out there, like deep speech, or let's say models from Google Cloud or Azure, AWS, probably using some form of CNNs in the backend. Generative learning is a whole other idea where you can, a lot of you may have used those styling apps where you can change the style of an image. So style transfer is where you can change the style of an image by applying the style from a source image into the content of another image. It's generative learning. You can use, again, convolutional neural networks here. You can build image or visual search engines where you can extract, as I said, features using convolutional neural networks and find out which images are similar to a source image. Image super resolution, again, another extension where you can improve the resolution of a base image, which has a poor resolution. Image captioning, I think a lot of you might be knowing about, where you can couple a CNN model with a generative language model and use it for image caption generation. So overall, these are some popular applications. Again, this is not an exhaustive list, but this should give you an idea about top use cases out there where CNN is being used. And that brings us an end to this session. Hopefully, this was useful. We had some minor glitches with the audio. Sorry about that. But again, a lot of this content is available online from some great resources in the form of courses, deeplearning.ai playlists, Coursera courses, some articles on towards data science, and so on. So do refer to these resources for more understanding and gaining more in-depth knowledge. And in case you have any kind of follow-up questions, we can obviously do a short Q&A here, but you can reach out to me offline on my GitHub, on my LinkedIn, and so on for further discussion if needed.
Great. Thanks a lot, Dipanjan. I think
Yeah.
the session went very well. So we have quick questions. So I'll go one by one. Doesn't the convolution already reduce the dimensions of the input? Why do we further reduce the dimensions through pooling?
So as I discussed, if you're not applying a stride, as you saw, 28 cross 28 only becomes 26 cross 26. So it's not really being reduced that much. The reason for using pooling is basically, as we discussed, to speed up the computation, preventing overfitting, making sure that the model converges faster, and obviously enhancing the key specific areas of the image and doing more effective downsampling, where you're almost reducing the image size by 2 every time. So.
Got it. And how do we combine the outputs from several layers for a single layer? Several filters for a single layer, sorry.
Several filters for a single layer. I don't get the question. Like, are we talking about specific inside one CNN or multiple CNNs? Because I mean, ultimately, if you remember that when we pass it through multiple conv pool layers, we end up with, let's say, 32 filters of, let's say, 5 cross 5. Then you can combine it using multiple operations. One is flattening. Then there are other things like global max pooling, global average pooling, and so on. So that is what I would recommend if you're looking at one CNN.
Okay, great. And then I think during one of the slides, you mentioned that, or during the hands-on, how does 6x6 matrix was converted to 4x4 with respect to 3 channels? I think this was a question asked by a couple of people. So
yes, so as we discussed before, this is what I think you might be talking about. So since we are using a 3 cross 3 convolution, it will start with the first 3 pixels here, and it will give you 1 pixel here. So let me try to get this for you. So if you see here, this is a 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So this is a 5 cross 5, and we are applying a 3 cross 3 kernel here. So you can see that for every 6 pixels, or every 6 pixels of the source image here, we are ending up with having 1 pixel. So what ends up happening is you lose the edges. of the image, basically, if you think about it like that. So similarly, if you apply this on the 6x6 and the 3x3 kernel, every 3x3 patch of the image becomes 1 pixel here. So you end up with that 4x4. The edges basically you lose, but if you added, let's say, one layer of outer padding here and you did a 3x3, then you would end up with kind of a similar dimension. So that is where the padding equals valid will keep it as reduced. But if you do padding equals same, it means keep the same dimensions as the image by padding it. So in that way, you don't lose the dimension, the outer edge, basically. Yeah.
And how do we combine the RGB convoluted matrices into single 2D matrix
So
by
this is
averaging across three
basically,
channels? Yeah.
yes. So basically, this is the answer to that question where you apply the same filter for R, for G, for B, and then you just combine it using a sum. You could do other things also, averaging and so on. Typically, sum is often used popularly. And in that way, you basically end up with a 2D feature map for that specific filter. And in that way, if you apply multiple features, you end up with multiple feature maps. But each feature map is a 2D tensor, by the way. It doesn't remain a 3D. Yeah.
Right. And is it compulsory to apply the same filter across all colors?
You could change it, though you would need to hack into the code, but typically, as far as I remember, the same one is used. But let's say if I only want to detect, so if you go to the original article here, I've changed the diagram a bit. In one of the depictions, he says that if you only want to apply edge detection on the R channel, then the others would be set to something else, let's say, or it would all be set to 0 or an identity. So that is possible, but you may need to hack into the code to do it. But theoretically, yes, it is possible. It's not like you always have to do the same.
And why max pooling is preferred over mean pooling?
So this is basically the answer for it. So various types of pooling are there. If you apply mean pooling, in many cases, it may work well. Again, based on the use cases I've worked on infrastructure data, on visual data, and so on, I have tried out mean pooling also. And that was way back when even TensorFlow 1 was in initial stages. So what I saw was mean pooling takes a lot of time to compute because, I mean, you just take a matrix and you try to do mean across multiple pixels and you do max across multiple pixels. You will see the compute is much faster for max. That is one thing. And the other thing is it usually ends up giving a better performance because it typically helps in enhancing the key aspects of those feature maps. If you remember where we visualize the edges of the shoe, so we don't really care much about the average pixels, but mostly like what is being highlighted. So that is where enhancing the key aspects of the feature maps works pretty well for max pooling, and that could be one of the main reasons as to at least what I've found. Yeah.
Okay, great. And is it necessary that we perform a manual operation for argumentation and pooling? Can't we do it using certain libraries?
Pooling we are not doing manually. Is it? Are you talking about augmentation is separate? Are you talking about
Yes, yes.
augmentation?
Yeah, yeah. It started with augmentation and also they mentioned pooling, but yeah, it was more
Yeah, yeah.
specific towards
Yeah,
augmentation.
so just to clarify, like the first notebook was to show you how things work behind the scenes, but we use, if you remember, the conv2D and the max pooling 2D API was from TensorFlow. So we don't want to code pooling manually. It doesn't make any sense because there are optimized things available. Image augmentation is another story. That is where we haven't shown it here due to the interest of time. But if you want to generate more images from a smaller data set, you could flip the images, crop it, rotate it, change the whitening, things like that. And that is where image data generator from Keras is very useful. There is another library called albumentations, if I remember correctly. So that is another library you could use out of the box for doing image augmentation.
Yeah. And can we use CNNs for multi-view clustering?
What do we mean by multi-view clustering? I don't know what multi-view means, but because maybe I haven't done that, but we have used CNNs a lot for clustering, where the whole idea is if you use CNNs as a feature extractor, you could use it for visual search, you could use it for clustering similar images together. You could even use it to detect outliers in images. So in that way, CNNs can definitely be used.
Great. And is it possible to reiterate briefly on how convolutional kernel apply on RGB images?
Yes, I know that is like can be challenging. So definitely go through this article. It's a good one, but the
Yeah.
basic idea is you start off with one filter, let's say 111.000.111 here, something like this. So basically RGB means 3 channels, and every channel is a 2-dimensional tensor or a matrix. Let's make things simple instead of using complex words. It's basically a 2-dimensional matrix of pixels, and you have 3 of these for R, G, and B. Take the same filter and you apply the convolution operation for R. Similarly, apply the same filter and do the convolution operation for G, and apply the same one for B and apply it across the blue channel of the image. And you end up with basically 4 cross 4 cross 3, let's say, where you have the feature maps for red, green, and blue. Take the sum, pixel-wise sum, and you end up with a 4 cross 4 feature map. So that is how you do the operation across R, G, and B.
Okay, got it. And yeah, how to avoid overfitting and underfitting in CNN?
So underfitting, yeah, underfitting depends again on your data totally. So there is no like generic methods, but if you see based on the learning curves that your training accuracy itself is not improving, could be multiple reasons. Maybe your images need more pre-processing. Maybe you haven't scaled the data in the right way. Maybe your architecture is not the best one. So all of these things you may need to check. Maybe you need to check the learning rate if necessary. And for overfitting, as discussed, you could use dropout, you could use batch normalization. Again, you could pre-process the images in a better way to remove unnecessary noise, background, and so on. And in these ways, you could try and help. And you could even introduce regularization in your model. So those are the ways to typically prevent overfitting.
Okay, great. And this is a more generic question. Transformers changed NLP forever. What is the next big thing in computer vision? What's your take on RL?
So transformers have changed definitely a lot. There is different types of models which have come out recently. I would recommend to check out Big Transfer from Google. They have even made these models available on TensorFlow Hub. I will maybe share some of this in the future. So there are state-of-the-art models even coming out for computer vision. Big Transfer from Google, Detectron from, I think, Facebook, and so on. So they are basically trying to adapt the transformer architecture into the vision domain also. So definitely, I think a lot of newer models are coming out even for vision. And we are even seeing more and more, I would say, domain and adaptation-based models coming out where you can apply, let's say, a CNN model for text detection, right, on images. You can apply a CNN model for table detection on digitized documents to do OCR, better OCR. So a lot of interesting things happening in the computer vision space, definitely, with regard to newer and newer models and more specific types of models being used for a wide variety of use cases.
Got it. And how to apply CNN in text classification in the main purpose of it? Yep.
Yeah, so that will take a more advanced NLP session maybe, but
Okay.
just briefly, you need a conv 1D filter to go across the text in sequence and apply that. You can check out my GitHub. There are many resources out there for actual hands-on code applying that. Yeah.
Got it. Can you please quickly cover, briefly cover fine-tuning part of transfer learning again, if possible? A very
Yeah,
brief
so
one. Yeah.
So basically, what fine-tuning means is when we take this model, which has been pre-trained on the ImageNet data set, each of these layers will already have some weights, right, for each of the neurons. Now, the whole idea here is try to change these weights based on passing your new input data through this, making the prediction, computing the loss, and backpropagating the gradients, basically. So when the gradients get backpropagated, each of the layer weights will change. And that is basically what fine-tuning is, where you are enabling the pre-trained model layers, you're opening them up and making them trainable. So that is all it means, that open up the layers, make sure that the weights of these layers change across the epochs, and they get fine-tuned to your own data. They learn representations based on your own data. You don't just use it as a feature extractor. And just briefly, again, coming back to the code, once you load up your model here using this, it means that it is loading the pre-trained weights from what it learned on the ImageNet data set. And then to open it up for fine-tuning, just set all the layers to true. Again, be careful here. I just did this for simplicity, but Typically, don't set all the layers to true just like that. Be very careful and be mindful also of the learning rate as we discussed here. Yeah.
Great. Before we end the session, we'll probably take last one or two questions. How to detect the duplicate images on the data set, as it will make the training bias?
Image deduplication is a nice way to go. I think there are a lot of libraries out there. You can just search image deduplication, but the basic premise of this is use a CNN, extract features of each and every image, obviously do some pre-processing, and then try to compute which images are very similar to each other. You could apply clustering, you could apply image similarity, nearest neighbors, things like that. And basically the images which start clustering together and which start looking very similar to each other or exact duplicates basically will have a really high similarity score and so on. So those are the ones then you could deduplicate and remove the duplicates.
Great. Yeah. Thanks. And last question. So for second convolutional layer, how is input shape same as first convolutional layer?
Input shape is basically not the same. I mean, as the first convolution layer, the input shape basically becomes what is the output of the convolution layer. So what that means is here we start with 28 cross 28, but when we are going into the second convolution layer, okay, this input shape, I think this maybe doesn't matter. Maybe I just copied this, so that could be the reason. But basically what happens is it just takes in this and then it plugs that in. That is what it happens. So I don't think this anyway applies here
Yeah.
from what I remember. So basically it's a hierarchical structure. So it starts with one input dimension, but as it goes through, every input, every output map or every output feature map becomes the input to the next one. So the dimensions basically of the output become the input in the next layer. Yeah.
Great. Thanks a lot, Dipanjan. I think it went really
Yeah.
well, and a lot of thanks
Yeah.
pouring in on the chat. Thanks a ton
Sure. Sure.
for yet another amazing session, and thanks a lot to all the amazing audience out there for being all throughout. Thanks a ton. And Dipanjan, any final thoughts on, like, any suggestions or inputs that you would want to give to the community in general? And yeah, that would be great, I guess.
Sure. Yeah, I would say definitely thanks for tuning in. I know it's a difficult time out there, but continuing to keeping to learn newer things and improve your skills, that is definitely important. And I can definitely see a lot of thanks in the chat and a lot of attendees. So I really appreciate all of you spending your time here, because time is of essence, right? And from a learning perspective, I would say whatever you're learning, like basically CNNs or anything for that matter, try to see what is out there, try to understand how things are being used, and then obviously try to understand things from an in-depth perspective also, like, okay, how does each and every specific layer work? And obviously do some hands-on, because if you just do conceptual learning, you will never be able to, like, let's say, apply it in real world scenarios. So basically do a mixture of everything, and that is what is going to help you forward. And definitely wishing all of you the best. And once again, thanks everyone for attending.
Thank you. Thanks, Dipanjan. Thanks a ton.
Yeah,
Yeah.
thanks.
Take care. Bye.